Chapter number 5, direct current motors. Let's discuss the principle of operation. We discussed the principle of operations, actually operation of motors in chapter number 2, where we discussed that motors operate on the basis of Lorentz force. That is, when a current carrying conductor is placed in a magnetic field, then the interaction between the current field produced by the current carrying conductor, the electric field, and the magnetic field produced by the flux or the magnet, the interaction between these two fields produces a force on the conductor. And if the conductor is free to move, either about an axis or free to move in the space, then under the action of this force, it starts moving. Of course, in the motors, conductors or armature, it moves about an axis because it moves in a circular motion. So the idea is exactly the same, and the construction of motors, basic construction of motors, is exactly the same as the basic construction of generators. The only difference between the motors and generator is that in generators, you put a load at the output, voltage is induced in the coil, and the output is connected to the load is connected to the commutator. And when you connect the load, of course, the induced voltage in the coil is going to run a current through the load. Here it's opposite. You still have the flux from the magnet or electromagnet, and then instead of connecting the load, you are connecting a power supply. So you connect a power supply which runs current in the coil. As you can see, the current is running into the page on the black side of the coil, and out of the page, that is under the north pole, out of the page on the white side of the coil. And current is always going to run in this direction because of the commutator. It's a DC motor. So this coil is going to experience a force. And in which direction coil is going to move? About the axis. Of course, axis is the middle line right here. This is the axis about which it is going to move. So which way it is going to move, you can always find out using F is equal to I L cross B. Right? So L cross B gives you the direction of the motion of the coil based on in which direction force is acting on the coil. So if the length vector, if the current is going, look at the first the north, the white side of the conductor under the north side of the magnet. Current is coming out. That means L vector is positive I, and B is positive J. So I cross J is K. So it is going to move. This side is going to move in the K direction. And likewise, the side which is black, it is negative I cross J is equal to negative K. So it is going to move in the negative K direction. So basically, this coil is going to turn in counterclockwise direction under the action of the current and the magnetic flux. And it's going to run with a specific speed, as we are going to discuss. Initially, of course, when there is no current flowing, that moment of that state is called the resting state. And then as soon as current starts flowing, of course, forces start acting, and then it starts rotating. Slowly it accelerates up to a point, what we are going to discuss next. Then when up to a specific point, and then the speed becomes constant, that it will just be cruising at that time. So initially it starts from 0, accelerate up to a speed at which it becomes constant, and then as long as there is no load connected, it will keep rotating at that speed. Once you connect the load, then of course what happens, we're going to discuss in the next few sections. So what is counter electromagnetic force, CEMF? Okay, so look at this picture. So this is your source voltage, this is your armature resistance. Alright, what is this E naught? So when the current is flowing in the winding and your armature start rotating, what's going to happen? The armature, the coil, will start cutting the magnetic field. And when the coil is going to cut the magnetic field, then according to the Faraday's law of electromagnetic induction, a voltage is going to be induced in the coil. That voltage is called counter electromotive force, CEMF. And why it is called counter? Because the direction of the voltage is such that it is opposite to the direction of the source voltage. So both of these, as you can see, both are positive, so they are cancelling each other. If you go in this loop basically and you calculate the current is going to be ES minus E naught over R. Right, so difference between ES and E naught, since they are in the same direction, divided by R. So this is counter electromotive force. When there is, and of course if it's a lap wound motor, then E naught, the induced voltage in the coil, can be calculated using Z and phi over 60. Go ahead and look at the example. So as I was mentioning, how does the motor accelerate? So from the resting point, when you connect it to the battery and you send the current for the first time, there is no counter electromotive force that is established in the armature yet, because it is not moving, right? That means this E naught is 0 at start, and the starting current can simply be measured by I is equal to ES over R. This is the starting current when E naught is 0. Now let's say armature resistance, as you saw in the last chapter, is usually very small, 0.5 ohm, 1 ohm, whatever, and ES, the source supply, can be 100 volt, 200 volt, whatever. So the initial current, starting current, is extremely large, extremely large, and it needs to be large because, again, if your motor is at rest and you have to push the motor, initially you need a large force that can put a large torque on the static conductors, right? Like if you're pushing a car, if your car is at rest and you have to push the car, initially you need a large force. Once your car starts moving, then you don't really need to push it that hard. You just need to push it a little bit so that it can overcome the force of gravity and the force of friction and all those, as long as you want to keep it moving in constant speed. Same thing with the motors. The initial torque, initial current is extremely large because you need the initial force initial current is extremely large because you need a large force and large torque to make it start moving from the resting point. Once it starts moving, it starts accelerating. Now what's going to happen? Counter electromotive force, CEMF, is going to start developing. So once CEMF starts developing, then your current in the armature starts going down. Initially, remember, E naught was 0. Now E naught starts increasing. ES is constant, R is constant. That means I starts going down. When the current in the armature starts going down, what's going to happen? The force, Lorentz force, starts becoming weaker. Now we can afford to have weaker Lorentz force once the armature is moving. Again, the same example as the car example. Once it starts moving, you don't need that much force to keep it moving. So as it speeds up, as it accelerates, E naught starts increasing because now the coils are cutting the magnetic field with a faster rate. So E naught starts increasing and armature current starts decreasing. Force, Lorentz force, start decreasing, and the torque on the coil starts decreasing. So when you have no load connected, then it will keep on accelerating. E naught will keep on increasing, I will keep on decreasing, force will keep on decreasing until it's going to be rotating at a rated no load speed. At that time, ES and E naught are very close to each other, extremely close to each other. The only difference between ES and E naught is a little bit of current that will produce a little bit of current, and that only little bit of current is required to produce a slight small force, Lorentz force, that will just keep it cruising at a constant velocity. to overcome some of the frictional forces and some miscellaneous forces, because now you don't need it to accelerate, you just need it to cruise. So if let's say if you don't have any friction force, actually you don't need any force, because remember Newton law say that a body in motion will be in motion, and a body is at rest will be at rest. But as long as there's the frictional force and some other miscellaneous forces, you still need to provide some force to keep it cruising at a constant speed. So at no load, ES and E naught are very close to each other. There is a small current flowing in the armature, which is which is enough to produce a small Lorentz force that will keep the armature cruising. So that's how motor accelerates up to a point where it is no longer accelerating and it starts cruising. At that time, E naught and ES are very close to each other, and there's a small current flowing in the armature to establish a small Lorentz force. Check out example 5.2. Mechanical power and torque on the motor. We know that the total armature power is given by the source, and it is the source voltage and the source current, product of source voltage and source current, ES, IS. We are assuming right now the motor is the field of the motor is not connected to the power supply right now. So total current that is coming out of the source is going, all the current is going in the armature. Soon we will see different types of motors, and of course, like we had the shunt generator and series generator, you will have the source connected to the field as well. In that case, of course, that is going to be ES times IA, total power that is supplied to your armature. Right now it's ES IS. We are assuming that the magnetism, the current which is producing the magnetism is not provided by the source voltage. So ES times IS is E naught plus ISRA, right? Because this is your, let me just draw it real quick. This is your ES, this is your RA, and this is your counter electromotive force. E naught, RA, ES, and IA. So ES is equal to drop in the armature resistance, E naught IS, and right here of course IA and IS are equal, and then the output power is E naught times IS plus the power dissipated in this resistance, which is ISRA IS. So ES is equal to E naught plus the voltage drop here, E naught plus the voltage drop in the armature resistance. So when you multiply that, E naught IS square RA, this is the output mechanical power. So this is the output power, which is the mechanical power. Remember, motor converts electrical power into mechanical power, and this is the power loss in the armature. So basically it converts into heat. So if I ask you anytime what is the power loss in the armature, that power loss is in this resistance, armature resistance. And what is the output power or mechanical power? That is the output power, which is the product of the CEMF, induced voltage, times the current that is passing through that, which is the armature current. In this case, armature current and source current is the same. So that's the output power. And we have the basic relationship of between the power and the torque, which is given by this equation. P is equal to NT 9.55. N is rotation of the armature in RPM, or rotation of motor in RPM. T is the torque, and 9.55 is basically a factor that they are using to balance some of the constant values. So P is E naught IS, so you can write down and then E naught is Zn phi over 60. So this is the basic relationship between P and T, and then T can also be written as Z phi IS over 2 pi, where 2 pi is 9.55 over 60, or 9.55 over 60 is 1 over 2 pi rather. So this is a simplified version in terms of the source current, the relationship of the source current and the torque. How much current is flowing? Of course, in the source current, or in this case, it's going to be armature current. How much current is flowing in the armature? Of course, torque is going to be related to that, since the armature current produces Lorentz force, and Lorentz force produces torque. So that's the mechanical power and torque of the motor. Let's also look at the speed of rotation. So when motor is running at the rated speed, and generally if you don't have any load connected, so this is pretty much at no load, then your your ES and E naught are very close to each other, as we discussed earlier. A very small voltage drop in the armature resistance. So as long as there is a very small voltage drop in the armature resistor, we can assume that ES and E naught are pretty close to each other. So we can write down E naught is equal to ZN phi over 60, or ES is approximately equal to ZN phi over 60. So from here, we see that number of conductors in the armature are not going to change unless you physically change the number of conductor. Flux is not going to change, because if you have a motor, separately excited motor, or any motor which is providing constant voltage to establish the field, and as long as that voltage does not change, the field current is not going to change, and your flux is not going to change. So if we keep flux and conductors to be constant, then you can see from this relationship that the speed of rotation is directly proportional to ES, or in other words, the speed of rotation is directly proportional to E naught, if again we keep the flux constant. Z is always constant. Now if we keep ES constant, ES is usually constant, or in other words, if we want E naught to be constant, or if ES and E naught are very close to each other, approximately equal. So if ES is constant, in other words, if E naught, the induced voltage or the CEMF is constant, then we can see that from the same relationship, we have ES constant, Z constant, 60 constant. So we have a constant equals N phi, and phi will be equal to K over N. In other words, phi will be inversely proportional to the speed of rotation, or a speed of rotation is inversely proportional to the flux per pole. Now this relationship is an extremely important relationship. That this shows that if for any reason, as long as your ES is constant, if for any reason your flux starts going down, something happens to the field and field starts becoming weak, and if the motor is running, what's going to happen? That motor is going to speed up, because flux is going down, the speed of motor is going up. So this is an extremely important relationship to remember, because we will use this relationship in several places. So two things: speed is directly proportional to the source voltage, or E naught, if source and E naught are close to each other, and speed is inversely proportional to the value of flux per pole. If it is going down, speed is going up. If the flux is increasing, speed is decreasing. The speed of rotation is decreasing. Alright, next we're going to discuss DC motor types.